All right, hello guys. So yes, I will not be showing my face because it's already like bloated. Okay, ayan. So this is probably the last video that I will give. So I will try my best to speak faster so that it will just be 1 hour. Wow. Okay, so this will already include enzymology, your electrolytes, and then toxicology. Of course, we will just be considering the basic things that you have to know first. Okay, ayan, mga basic lang tayo guys. So that during our pre-exam ratio, so that's the time that I will be adding more. Okay. So first, let's talk about your enzymes. One of the simple questions that they asked about enzymes is, what type of biomolecule are your enzymes? Okay, so very easy, very basic. Okay, so take note, class, that your enzymes, they are considered to be specific, diba? Biologic proteins that catalyze, okay, that catalyze biochemical reactions. Okay, yes. So in short, if you will be asked what type of biomolecule are enzymes, they are considered to be proteins. Okay, so please do not forget, they are considered to be proteins. Tama? Okay, sige, lagyan natin ng stamp. Okay, so they are considered to be proteins. And then, again, another recall question is, how? Diba? How are you? Biglang, how? Okay, how do your enzymes catalyze biochemical reactions? Okay, so take note that your enzymes catalyze biochemical reactions by, okay, so take note, by lowering the activation energy of the reaction. Okay, so when we say activation energy, so this is the energy needed in order for the reaction to progress or to start. Okay, so by lowering the activation energy, your enzymes are able to catalyze your biochemical reactions. Okay, ayan. So another basic knowledge that you have to, yes, that you have to know about your enzymes would be the different factors that influence enzymatic reactions. Okay, so first, of course, we have your first order kinetic. Okay, first order kinetics, and then the other one is your zero order kinetics. Okay, so yan. So let me just write it here. So the first one would be substrate. Okay, substrate concentration. So in the case of your substrate concentration, so the concepts on first order kinetics. Okay, so we have your first order kinetics and your zero, okay, order, your zero order kinetics will, of course, be considered when it comes to your substrate concentration. Okay, take note ha, ganito lang yan. Very easy to understand. So when we talk about your first order kinetics, take note that the enzyme in this case is or has a higher concentration as compared to your substrate. Okay, yeah. So first order kinetics, enzyme has a higher concentration as compared to your substrate. That's why if we are talking about your first order kinetics, the rate is, okay, proportional. Okay, the rate is proportional to your substrates. Okay, to the concentration of your substrate. Why? Why kaya? Bakit kaya substrate ang magdedetermine ng first order kinetics? In English, why would the substrate be the one that will ang pangalan nito, that will determine the rate in your first order kinetics? Because it is the limiting, 'di ba? It is the limiting factor in your first order kinetics. That means you don't have any problem with your enzyme. Right? Your enzymes, all of your enzymes, all the necessary concentration of your enzyme is there, is present in the environment or is present in the reaction. So you don't have a problem with your enzyme. The problem is in the concentration of your substrate. Okay, so that means if you increase, if you increase the concentration of the substrate, then the rate will also increase. If you decrease the concentration of your substrate, then the rate of reaction will also decrease because it is the limiting factor in your first order kinetics. Okay, so in contrast, class, when we talk about your zero order kinetics on the other hand, so in zero order kinetics, your substrate is greater than your enzyme. Okay, yes, so your substrate is greater than your enzyme. Therefore, what is our limiting factor? It's your enzyme. You don't have a problem with your substrate concentration. All of the necessary substrate is present in your reaction. Okay, ayan. Wala kang problema sa substrate. So, in this case, for your zero order kinetics, rate is proportional to your enzyme, which is considered as the limiting factor. So that means in zero order kinetics, if you increase the number or the concentration of your enzyme, then the rate will become faster. If you decrease the concentration of your enzyme in zero order kinetics, then the rate will also decrease or it will become slower. Okay, so as easy as that. So you just have to identify what is the limiting factor in that particular kinetics. Okay, yes, ganun lang siya. And the limiting factor would always be the one that is not adequate. Okay, ayan, 'di ba? Just like in ano naman in life, in life, the limiting factor would always be the one that we don't have or that we have in small amounts. Okay, so yan. So please just remember what is the limiting factor, then that will be the one to determine the rate of your enzymatic reaction. Okay? Ayan. So another would be the presence of your cofactors. Okay, so yan, dito na tayo. All right. So they would always ask about your first order kinetics and your zero order kinetics. So please review this one. So for your cofactor on the other hand, so remember that there are reactions in which your enzymes will not be able to act on its own. Okay, so there is a need for you to factor in another component of your enzymatic reaction or your enzyme in this case, and that is your cofactor. Okay, so when we say cofactor class, yes, of course, we have to know the definition. This is a non-protein molecule that is needed for enzyme activity. So it participates in the reaction. Okay, so take note that your cofactors, they have to be present in excess. Okay, so cofactors, they have to be present, okay, in excess. Alright, ayan. So that is one important thing that you have to consider, the concentration also of your cofactor. So there are two types of cofactors. Yes, we have your activator. Okay, so the first one, we have your activator, and then the other one is your coenzyme. Okay, so what's the difference? Very easy. So when we say activator, so these are inorganic. Okay, so these are inorganic cofactors. So when we say inorganic cofactors, these are basically our elements, 'di ba? Our electrolytes. Okay, our heavy metals, 'di ba? All right. So examples of inorganic cofactors, or yes, inorganic cofactors or activators, we have chloride. Okay, we have magnesium. Okay, so these are examples of activators. So whenever you see electrolytes as your cofactors, we refer to them as your activators. Okay, so another, take note that in the case of your activators, they work by either, yes, by either enhancing the reaction or they are required by the reaction. Okay, yes. So it's either your activators are required by the reaction, or enhance the reaction. Okay, yes. So in contrast, when we talk about your coenzyme, all right. So when we talk about your coenzymes are organic cofactors. So examples of organic cofactors, we have vitamin B, di ba? Your pyridoxal phosphate, vitamin B12, di ba? Your pyridoxal phosphate, that is an example of a coenzyme. Another very common coenzyme that is utilized for or in our reactions, we have your nicotinamide adenine dinucleotide. Okay, so in the case of your nicotinamide adenine dinucleotide, or in the case of your organic cofactors or coenzymes, they usually serve as additional or as the second substrate. Okay, yeah. So they serve as the second substrate in the reaction. Yes. So remember, 'di ba? In most of the enzymatic reactions that we have, it would usually involve the interconversion, 'di ba? When we say interconversion, so the reaction is basically reversible. So the interconversion of your nicotinamide adenine dinucleotide to its reduced form, which is your reduced nicotinamide adenine dinucleotide. Okay, ayan. So that is how you are going to read your NADH, reduced nicotinamide adenine dinucleotide. Okay, yes. And most of the reactions that are utilized for the determination of our enzymes would be or would involve the conversion of your NAD to its reduced form, NADH. Why kaya? Yes, why kaya? This is because take note that your NADH has an absorbance at 340 nanometers. Okay, so this is basically the reason why NADH is preferred over your NAD. Okay, what we are trying to measure is either the formation of your NADH or the disappearance of your NADH in or at 340 nanometers. Mapapansin nyo yan. You would be able to observe that in the different enzymatic reactions. Okay, that are involved in the assay of your enzymes. Okay, so either lang, dalawa lang yan talaga. Either appearance of your NADH or disappearance of your NADH. Okay? And so another topic that's important when it comes to your enzymes would be enzyme classification and nomenclature. Yes. So during our 2021 board exams, they were asked about the classification of your enzymes. So during the 2022 January board exams, they were asked about the nomenclature or the naming of your enzymes. Okay, so first, of course, let us discuss. Okay, uh, let us discuss the different classes of enzymes. And of course, you have to write it in this manner because enzyme classification will affect enzyme nomenclature. Okay, so you cannot jumble the different classes. You have to write it in this manner. Number one would be your oxidoreductase. Number two would be your transferase. Number three would be your hydrolase. Number four would be your lyase. Number five, we have isomerase. And then number six, we have ligase. Okay. So, you don't necessarily have to memorize the tables provided by our references in order for you to classify the different enzymes that we have. So, probably you can memorize just a few, okay? Because there are actually clues as to what enzyme class a specific enzyme belongs to. Okay, like for example, if we consider your oxidoreductase, okay, so these enzymes catalyze oxidation reduction reactions. Tama? Oxidation reduction reactions. Okay? So when we say oxidation reduction reactions or redox reactions, this would involve either the removal or the addition of your electrons. So this is from your general chemistry, right? Okay, we have your redox reactions. Okay, so what will be our clue when it comes to your oxidoreductase enzyme? So let's take a look at the examples. So the examples, we have lactate dehydrogenase and then glucose 6-phosphate dehydrogenase. So that means when you see the acronym DH, okay, which basically stands for dehydrogenase, then automatically it is an oxidoreductase enzyme. Okay, yes, and it is classified as class 1 enzyme. Okay, another, we have your transferase enzyme or transferases. So they catalyze the transfer of a group. Yes, so they catalyze the transfer of a chemical or functional group from one substance to another. Okay, so there are only two groups, okay, commonly transferred by your transferase enzymes. So it's either your amino group or we have your phosphate group. Okay, and of course, depending upon the group that is being transferred by your enzyme, we also have clues as to the naming of your enzymes. Okay, so of course, when we talk about your amino, okay, amino group is transferred by our transaminases. Diba? It's quite obvious. Okay, so amino group, so this is transferred. Okay, so this is being transferred by our transaminase enzymes. Or some of them are now referred to as your transferase enzymes. Okay, so when you see a particular enzyme with the name transaminase or transferase, automatically, of course, it's a transferase enzyme transferring amino group. Okay, transferring an amino group. So examples, we have your AST, ALT, and then we have your GGT, all of which are transferase enzymes. Like for example, di ba, AST. What is AST? Aspartate aminotransferase. Okay? ALT. ALT is your alanine aminotransferase. What else? We also have your GGT, di ba? GGT is gamma glutamyl transferase or gamma glutamyl, yeah, tama. Okay, transferase. All right. And then the other one, we have your phosphate group. So what will be our clue if a particular enzyme transfers a phosphate group? So you look for kinase. Okay, so if there is the word kinase in the nomenclature or in the naming or name of your enzyme, then automatically it is a transferase enzyme, okay, transferring a phosphate group. Okay, ayan. So another, we also have our hydrolase enzymes. Okay, hydrolase enzymes. So from the term itself, these enzymes catalyze the hydrolysis of various bonds. Okay, so since we are talking of hydro, okay, hydrolase. So this would involve the introduction of water into the structure. Okay, catalyzes the hydrolysis of compounds with the introduction of water into the structure and cleavage of bonds with water. Okay, ayan. So, hydrolysis or hydrolase enzymes, so they are mostly our enzymes of digestion. Okay, like for example, we have amylase. Ayan. We also have lipase. So these are examples of hydrolase enzymes. So we also have cholinesterase, okay, and our phosphatases. Okay, so we have your alkaline phosphatase and then your acid phosphatase. Okay. Another, we also have your lyase. So your lyase, it catalyzes the removal of groups. So examples, we have aldolase, pyruvate decarboxylase, glutamate decarboxylase also. Okay, so take note that when you see the term decarbolase, decarboxylase, sorry, then it is automatically a lyase enzyme. So for the next one, they're very easy to classify because in their names or nomenclature, you would be able to see there the term isomerase. Okay, so isomerase enzymes catalyze the interconversion of your isomers. Okay, yes, of your isomers. So in short, they are responsible for the intramolecular rearrangement of your substrate compounds. Okay, so from one isomer to another. So if you're going to look at their names, we have glucose phosphate isomerase, ribose phosphate isomerase. So they're quite easy to identify. Okay, and then the last one, we have your ligase. So ligase enzymes catalyze the joining of two substrate molecules in order to form a larger molecule. Okay, ayan. And in this case, our clue is the term synthetase. Okay, so basically what you are doing if you're going to use ligase in a particular enzymatic reaction would be to synthesize a larger molecule from smaller ones. Tama, ayan. So you look for the term synthetase, meaning synthesis of a larger molecule. Okay? So in the board exam, they were able, ang mga recall questions natin, our recall questions in the board exam would be your LDH, and then transferase, and then we have your aldolase. Okay, ayan. So they would usually ask, which of the following are transferase enzymes? Or lactate dehydrogenase is an example of ganun. Okay, so that is how they are going to ask you in the board exam. All right, and of course, it might evolve. right, into something that will now incorporate the nomenclature of your enzymes. So particularly, they asked already about your EC numerical code. Okay, di ba? We have your EC numerical code. So remember that your EC numerical code, so they are represented by 4 numbers. Tama? So they are represented, okay, represented by 4 numbers. Tama? Okay. And of course, separating the 4 numbers would be your dot or your period. Okay, like for example, so let us take into consideration one easy number. Sige, ano tayo ng easy number ha? Yes. So actually, ngayon lang ulit nila nilabas. Okay, so they asked about this only now. Yeah, only now. Only now again. Okay, because I remember when I was reviewing for the board exam, they asked us to memorize the easy numerical code. I even remember my CI when I was an intern at UBCL. We were asked to memorize all of the easy numerical code. But of course, I forgot it already. Okay. Ayan. So, in the board exam, last January, what represents or what is the what ano ba yan? what okay, what what do the different numbers represent? Okay, yeah, I just forgot the exact recall question. It's something like that. Okay, so remember that when we talk about your easy numerical code, so this is how it is presented in our references. So I will just make use of the term digit. Okay, so first digit, di ba? Wait, we have our first digit. So the first digit represents your enzyme class. Okay, so this is your enzyme class. Okay, and then we also have the second digit. The second digit is represents the subclass. Okay, and then we have our third digit. So the third digit represents your subclass. Okay, and then of course we have the last one. We have the fourth digit. So this is the serial number. Okay, this is the serial number that is specific to the enzyme. So that means, no easy numerical code is the same. Okay, the easy numerical code of our enzymes are different from one another. This is because of the fourth digit. Okay, the fourth digit, this makes enzyme nomenclature or the naming of your enzymes unique, okay, from one another. All right, so please do not forget that. And then, of course, say for example, sige, mag-example tayo ha. Say for example, in the case of your ALP. So what is the easy number of your ALP? So we have 3.1.3.1. All right. So as you can see, that's why I asked you to memorize, diba? Memorize your enzyme classes in this manner because, as you can see here, so this is the first digit. So ALP is what type of enzyme? It's a hydrolase enzyme. And you would be able to see there number 3. Okay, so number 1, that's your subclass. Number 3, again, that's your subclass. And then number 1, so this will make your easy number unique because this is unique to your ALP. Out of all the hydrolase enzymes or out of all the enzymes belonging to the hydrolase group. Okay, so only your ALP is designated as number 1. Naku ha, yan. So your ALP, this is designated as your number 1. Okay, yes. For your ACP, on the other hand, the easy numerical code of of ACP is 3.1.3.2. Okay, so as you can see, yes, as you can see, the identifying digit is the last one because this is specific to the enzyme in that particular class. Okay, ayan. So as the first three digits are the same, diba? The first three digits are the same, meaning your ACP and your ALP belong to the same class. They belong to the same subclass. They belong to the same sub-subclass. Okay, yes. However, number one, that is specific to your ALP. Number two, that is specific to your ACP in this particular sub-subclass. Okay, ayan. All right. So that is how we interpret the EC numerical code. Okay, so it is actually the most systematic manner by which we can name our enzymes. Okay, so please do not forget. So now I have listed some important enzymes that we have to discuss. So first we have our AST. So AST, what is the old name of your AST? Yes, of course. The old name is serum glutamic, okay, oxaloacetic transaminase. Yan. So serum glutamic oxaloacetic transaminase. So the old name will tell us the reaction that is involved. So as you can see, your AST, it is involved in the reversible reaction between aspartate and your alpha ketoglutarate to form your oxaloacetate and your glutamate. Okay, ayan. So take note, class, that your AST, yes, AST is primarily utilized in the clinical setting in conjunction with ALT for hepatocellular. Okay, so for your hepatocellular damage or disorders. Okay, hepatocellular damage or disorders. Okay, ayan. So, yeah, actually, I will be teaching you how you're going to interpret your enzymes. Okay, let's make it simple so that you don't necessarily have to remember everything. Okay. So, you know, our pair of enzymes, especially when it comes to evaluating your conditions of, conditions involving your liver. Yes. So when we say hepatocellular damage, the two pair or the two enzymes that are utilized, we have your AST and ALT. Okay. However, if we talk about your hepatobiliary damage, okay, the two enzymes that we can assay, we have your ALT as well as your GGT. All right, ayan. So what are examples of hepatocellular damage? So we have your cirrhosis, yung mga yan, okay? So those are, yung mga yan, isa lang yung binigay, okay? That is an example of a liver disease affecting the cells of the liver. Okay, hepatocellular damage. And then when you see there, hepatobiliary damage, like for example, we have obstruction. Okay, so that the two enzymes that are needed in order to aid in its diagnosis would be your ALT and your GGT. Okay, yes. So let's go back to your aspartate aminotransferase. Okay, so there is a particular method that is utilized for your for the determination of your AST. So we have your Carmen method. Okay, yes. One method is your Carmen method. So this incorporates a coupled enzymatic reaction. So yes, one of the questions that was asked also in the board exam is the coupling enzyme. I just forgot kung anong analyte yon. Okay. However, since they already asked about our coupling enzymes, so I suggest that you start reviewing or start memorizing, not really memorize, yeah, but memorize, okay, your coupling enzyme. So the coupling enzyme for your AST determination in your Carmen method is your malate dehydrogenase. I think AST yata yung tinanong eh. Okay, yes, malate dehydrogenase. This is the coupling enzyme. So class, if for example, they do not make use of your coupling enzyme as the term, so please take note that in this case, for coupled enzymatic reactions, uh, malate dehydrogenase is also referred to as the indicator enzyme. Kasi baka mamaya, they will not make use of coupling enzyme. Okay, so please take note, it's the coupling, okay, or the indicator enzyme in your Carmen method for AST. We have your malate dehydrogenase. Okay, yes. So basically, ma'am, what is the principle behind your Carmen method? In your Carmen method class, okay, in your Carmen method, um basically what we are trying to measure is a decrease, okay? Yes, we are trying to monitor or to measure the decrease in the absorbance, okay? Decrease in the absorbance of, yes, very good, your NADH. This is the reason why I usually give generalization so that you don't necessarily have to memorize everything. Oh, NADH. Again, at what particular absorbance do we measure your NADH? It's 300 nanometers. Okay, so in the laboratory, at what wavelength do we use in order to assay your AST? O sa mga, for those who have already experienced performing AST and ALT determination in the laboratory, we have 340 nanometers. Okay, ayan, all right. So take note ha. Okay, do not forget. Okay, sorry. Okay, ayan. Yeah, kasi dapat magbigay pa ako ng iba eh. Hepatocellular damage, we have your cirrhosis, what else? We have your hepatitis also. Yan. So those are examples of your hepatocellular disorders. Okay, yes. So in the laboratory, its application nowadays, it's really in your hepatocellular disorders or diseases. Historically, it was used for your AMI, your acute myocardial infarction. However, yeah, that's a recall question also in the board. However, if it will be asked, which of the following enzymes is not, ganun yung recall question, that's the recall question in AST. Which of the following enzymes is not measured for AMI? The correct answer is your AST. Okay, because it has only a historical significance, but now we don't measure it anymore because there are other enzymes that you can use actually instead of your AST. Okay, and be correlated to your acute myocardial infarction. Okay, siya na hindi ginagamit. It is the one that is no longer utilized. Okay, next. Wait a minute. I'm just gonna erase. Okay, so next we move on to your ALT. Yes, ALT or your alanine aminotransferase. Okay, so take note, class, that your ALT, so the old name is serum glutamic pyruvic transaminase or your SGPT. Okay, yes. So it catalyzes the reaction between alanine and alpha-ketoglutarate in order to form glutamate and pyruvate. Okay, in order to form glutamate and your pyruvate. Okay, so actually there is also um uh your ALT rather is also used for liver disease. So in particular, we have your hepatocellular damage, right? If we are going to compare the specificity of your AST as compared to your ALT, Which one is more liver specific? It's your ALT. Okay, yes, it is your ALT. And take note, the highest elevation of your ALT is seen in acute liver hepatitis. Okay, it is seen in acute liver hepatitis. Okay, yan. So anything that will affect your liver cells. Okay, yes. Your liver cells will have an increase, di ba, in your ALT. Okay, ayan. So basically, there are two methods that are utilized in the laboratory. Yes, let me mention Frankel, Frankel, okay, because this has been asked in the board exam. So the enzymatic method, okay, the enzymatic method for your alanine aminotransferase. So if we have Carmen for AST, then we have Walker. Okay, we have Walker. Okay, wait lang ha, wait lang. Wait lang po. Kasi may makulit sa labas. All right, ayan. So let's continue. Okay, so we were discussing about your coupled enzymatic reaction. Okay, so the coupled enzymatic reaction for your ALT, so it is referred to as your Walker method, not Walker. Okay, Walker method po. Okay, Walker method. And your Reitman-Frankel method, so this is the chemical method in which this would involve, okay, the reaction with your DNPH or your 2,4-dinitrophenylhydrazine. Okay, yes, so 2,4-dinitrophenylhydrazine. So actually, your AST, okay, your AST, there is also a laboratory method in which your AST or the keto acid that is formed is allowed to react with your diazonium salt. So that is the alternative method for your AST determination. Okay, so first, balik tayo sa ALT. So for the coupled enzymatic method, for your ALT, okay, so take note that the coupling enzyme or the indicator enzyme that is utilized is your lactate dehydrogenase or your LD or your LDH. Okay, so we have your lactate dehydrogenase. So again, for your AST, what is the coupling or the indicator enzyme? We have your malate dehydrogenase. Okay, ayan. So, for the enzymatic reaction, so it's the same. What are we monitoring? So, we are monitoring the decrease in the intensity or in the absorbance rather of your NADH. Okay, so again, at what particular wavelength do we measure your NADH? We have 340 nanometers. Okay, yes. So another method for your ALT, just like what I have mentioned, we have your Reitman-Frankel method. Okay, so this would involve a reaction with your DNPH. If I'm not mistaken, the meaning of DNPH was already asked before. So take note that the chemical name of your DNPH is 2,4-dinitrophenylhydrazine. Okay, at dinitrophenylhydrazine. All right, so that is the chemical name of your DNPH. Okay, and upon reaction with your 2,4-dinitrophenylhydrazine, so this will now form a keto acid hydrazone. Okay, so this will form several molecules of keto acid hydrazone, which will produce an intense brown color. Okay, brown color in the presence of sodium hydroxide. Okay, yes. The problem with your Reitman-Frankel method is that it is not specific. Okay, it lacks the specificity that your enzymatic method has. Okay, all right. So now let us move on to ano ba ba? Okay, so ELT for hepatocellular. So this is for your hepatocellular disorder. Okay, so we have your hepatitis. What else? Diseases that would involve your liver parenchyma or your hepatic parenchyma. All right, so those. Okay, okay, so let us move on to the next one. So we have your lactate dehydrogenase. Okay. Yes. So sometimes the question in your lactate dehydrogenase is just simple. Like for example, okay, recall question from the board exam. What is the most cardiac specific LDH? Okay, so take note also that your LDH, it has how many isoenzymes? It has 5 isoenzymes. So we have your LD1, LD2, LD3, LD4, and LD5. And if we are going to look at the structure of your LDH, okay, of your lactate dehydrogenase, it is considered to be a tetramer. Tetramer because it is composed of 4 subunits. Tama? Okay. So the subunits of your LD enzymes, your lactate dehydrogenase enzymes, we have your H subunit. H stands for heart. And we have your M subunit rather. So M stands for muscle. So let us look at the different isoenzymes. Yes. So by the way, class, again, how do we separate the isoenzymes of your enzymes, okay, or the isomers of your enzymes? It is via electrophoresis. Okay, so the naming, therefore, of your enzymes, like for example, LD1, LD2, LD3, LD4, and LD5, so this would pertain to their electrophoretic mobility. So of course, one being the fastest. Okay, ganun naman lagi, di ba? Of course. All right. So if we are going to look at the LD1 isoenzyme, so again, lactate dehydrogenase enzyme isoenzymes are tetrameric. They're composed of 4 subunits. So LD1 is composed of 4 H subunits. Thus, okay, LD1 is considered to be the most cardiac specific. Okay, another, we have LD2, HH, triple H, M. Okay, and then we have LD3, double H, double M. Okay, and then we have LD4, okay, 1H, and then triple M. And then lastly, we have LD5, which is composed of 4 M subunits. Okay, so the most cardiac specific is, of course, your LD1. Okay, yes. So now, let us move on. Ay, hindi ko pa pala nababanggit. So what is the type of reaction that your lactate dehydrogenase enzyme catalyzes? So it catalyzes the reversible conversion of lactate and NAD into pyruvate and NADH. So I guess you know what are we trying to measure here, di ba? Okay. So, eto pa ha, this was asked also in the board exam, okay? So take note that even if the isoenzymes of a particular enzyme for that matter, even if their structures are different from one another, they catalyze the same, okay, the same reaction. And that is the reversible conversion of lactate and NAD into pyruvate and reduced NAD. It's the same reaction regardless of the structure. Okay, yeah, so please do not forget the same reaction. So whether we are talking about LD1, LD2, LD3, LD4, or LD5, it's the same reaction. Okay, yes, their only difference is that Of course, they have different structures. They have different subunits. And because of these differences in the subunits, they are also different when it comes to the type of organ in which they are seen. Like for example, LD1. Diba? LD1 is seen in cardiac tissue. Tama? LD1 is seen in your cardiac tissue. Okay, yes. And then, actually, if you're going to look at your lactate dehydrogenase, yes, it is considered to be a non-specific enzyme. Okay, because it is ubiquitous. It is found in a lot of tissues, a lot of organs. Yes, it is not specific. Okay, it is not specific po. All right. Okay, so let us take a look at the electrophoretic mobility. So just like what I have mentioned, from the cathode to the anode, the fastest one to migrate is your LD1, followed by your LD2, LD3, LD4, and then LD5. So that is actually the number that is incorporated in the name that would actually be or that would actually refer to its electrophoretic mobility. Laging one ang nauuna, di ba? Where do you see naman that one is not the first? Of course, one would always be the first and it would always be the fastest. Okay, yeah, so that's the electrophoretic mobility. However, if you're going to look at the concentration of lactate dehydrogenase in normal serum or in the serum of normal individuals, okay, the highest concentration is your LD2. Okay, followed by LD1, LD3, LD4, and LD5. So the least, di ba, the least concentrated isoenzyme of lactate dehydrogenase, we have your LD5. Okay, so of course, this has a significance if we are going to correlate the values of your lactate dehydrogenase isoenzymes to the occurrence of acute myocardial infarction. So remember that in acute myocardial infarction, we have what we call your flipped pattern. Okay, so we have what we call your flipped pattern. Okay, so flipped pattern because instead of LD2 having the highest, sorry, so flipped pattern. Okay, so do not forget the flipped pattern. All right, so why? Because instead of your LD2 having the highest concentration in the occurrence of an acute myocardial infarction, your LD1, okay, becomes greater than your LD2. Why? Guys, I mentioned already, LD1 is the most cardiac specific. So you would be able to see it in its subunits. It is composed of 4 heart subunits. Okay, yes, of course, if you have a lot of heart subunits, then automatically that's the most cardiac specific. And what happens by in AMI? Remember that in AMI, there is destruction of your myocytes or your muscle cells, which, yes, is a mechanism on how your enzymes would increase in your circulation. So if cells are destroyed, so this will result to the liberation of the enzymes found inside your cells. Okay, yes, such as what happens in your AMI. So since LB1 is the most cardiac specific, so it will now override the concentration of your LD2, leading to a flipped pattern. Okay, ayan. But the highest elevation of your lactate dehydrogenase class, remember, it is seen in pernicious anemia or in megaloblastic anemia. Okay, so pernicious anemia or your megaloblastic anemia. Okay, yes, megaloblastic and your pernicious anemia. So particularly the enzyme that is involved in this condition, we have your LD2. Okay, we have your LD2 enzyme. Okay. So now let us go to the laboratory method. So first we have your Walker Yes, Walker method. So your Walker method. So this is the forward reaction. Okay, yes. So this is your forward reaction. Okay, the forward reaction meaning, ano ba ang forward reaction natin dito? So meaning, this would involve, okay, your lactate, tama, your lactate plus your anong pangalan nito? Lactate plus your NAD, okay, which will form now your pyruvate, diba? Pyruvate plus reduced NAD. Okay, so we have reduced NAD. So that is the forward reaction. So as you can see, if there is the production of your NAD, so the basis for measurement would be the formation of your reduced NAD. Okay, what absorbance? Oh, do not think na kasi it's 340 nanometers. Kasi we're talking about NAD, reduced NAD here. Diba? We're talking about reduced NAD. Okay? So the color that is produced in this particular reaction, we have blue-purple. Involves the formation of a blue-purple color or chromogen. Next, we have our Roblewski-Ladu. So our Roblewski-Ladu, so it involves naman, okay, the conversion, the reversible reaction. Yes, the reverse reaction rather. Yes, the reverse reaction is or starts rather with your pyruvate plus your reduced NADH. So this will now be converted to lactate plus your NAD. And so what is our basis in the measurement of your enzyme activity? Very good. Okay? Very good. So we have a decrease, di ba? Or a disappearance of your NADH, meaning a decrease in the absorbance of your NADH is measured at what wavelength? Again, NADH, hello, 340 nanometers. Okay, ayan. So, 340 nanometers pa din. And then, ito pa, another recall question from the board exam. What is the most, anong tawag dito? Cold labile. That was the term that was used. What is the most cold labile lactate dehydrogenase isoenzyme? We have our LD5. Okay, thus, if you are going to measure your lactate dehydrogenase in the enzymes, specimens, okay, should not be frozen. Yes, you have to be careful because remember that when it comes to the storage of specimens, especially for clinical chemistry, what do we usually do? We freeze. Diba? That's the common general storage of your samples in clinical chemistry. However, again, if you are going to measure your lactate dehydrogenase, specimens should not be frozen. Therefore, yes, specimens should not be frozen, and specimens should be stored at room temperature. Okay, they should not be frozen. They should instead be stored at room temperature. Okay, ayan. All right. So those are the things for now that you have to remember for your lactate dehydrogenase. So very easy. Okay, next. Wow, very, very easy ka dyan, ha? I'm sorry. Okay. Next, we have our creatine kinase. Okay, yes. So creatine kinase class, this is what example, what enzyme? Yes, very good. We have transferase enzyme. So it catalyzes the transfer of phosphate to creatine. Sorry, transfer of phosphate to creatine. So it is actually involved in the phosphorylation reversible phosphorylation of your creatine. Okay, in order for you to form ATP. So take note that the activator that is needed for your creatine kinase is your magnesium ion. Okay, we have your magnesium ion. Okay, yes. All right, so when it comes to the isoenzymes, yes, the isoenzymes of your CK, they are actually considered to be dimeric. Diba? They are dimeric, yes. And um, via electrophoresis, we are able to separate three isoenzymes of creatine kinase. So we have your CK1. So this is otherwise referred to as your CKBB. Okay, this is otherwise referred to as your CKBB. B stands for brain. Okay, so of course, if they will ask what is the most brain-specific CK, it's CK1 or CKBB. All right, so another, we have your CK2. So CK2, so this is your CKMB. Okay, so basically your CKMB, so this is the most cardiac specific. All right, yes. And then we have CK3. Okay, so this is otherwise referred to as your CKMM. So please do not be mistaken, ha. M there stands for skeletal muscle. Okay, the muscle there refers to your skeletal muscle. Okay, because we have already identified H, diba? H to be your heart in your LBH. Okay, yes. So that means for your CK1, so it is more predominant in the brain. Your CKMB, this is the one that is cardiac specific. CK3, so this is usually seen in your skeletal muscle. Okay, skeletal muscle siya. All right. So as for the electrophoretic mobility of your creatine kinase, we follow the same. So, di ba, what should be number one? What should be the fastest? Or what should come first? We have your CK1. Okay, CK1 and then followed by your CK2 and then your CK3. Right? So take note that your creatine kinase highest elevation is seen in your Duchenne. Okay, Duchenne's muscular dystrophy. I checked, it's Duchenne. I think it's French. Yeah, I forgot na. Okay. Okay, so it's Duchenne's muscular dystrophy. So highest elevation. All right. Specimen consideration when it comes to your creatine kinase, no to hemolysis. Okay, why? Because remember that although your RBC or your CK is not present in your RBC, there is a similar enzyme that catalyzes the same reaction. So we have your adenylate kinase. Okay, so your adenylate kinase, so this is an enzyme that has a similar catalytic activity to that of your creatine kinase. And of course, if there is hemolysis, then you have a lot of adenylate kinase in your serum or in your plasma. So this will now tend to catalyze the same reaction, yes, and it will lead to a false increase. Okay, so it will lead to false increased levels of your CK. But it's not your CK, it's your adenylate kinase. Right. Another consideration when it comes to the assay of your CK is that it should be protected from light. Okay, so why should it be protected from light? This is because take note that your CK is inactivated by light. Okay, so remember that there are two things that you have to consider when it comes to your enzymatic assays, okay, or your enzyme assays rather. Okay, number one is that, of course, the enzyme has to be there. Okay, but in addition to the presence of your enzyme, you have to ensure that your enzyme is active. Diba? Yes, your enzyme should be active. Because this is because what we are measuring is activity of your enzyme, not just the presence of your enzyme, but its ability to catalyze your reaction. Okay, so of course, if for example, your enzyme becomes inactivated by a certain factor, would you still be able to measure it? No. Okay, you would not be able to measure it even if it is present in high concentrations. Okay, it will no longer be able to catalyze the reaction because it is inactive. Okay, ayan. So another, we have the laboratory methods that are utilized. Oh, andito na naman si NAD dash. Okay, so buti na lang, di ba? Alam na natin na ang buti na lang, good for us because we already know your NAD and your NADH. Okay, so this is the reason why you always have to find a common ground or a denominator, okay, in whatever topic you are trying to review so that you don't have to memorize everything. Tama? Yes, you don't have to memorize everything po. Wait a minute. Okay. Nag-continue ba ito? Yeah, I think so. Okay, so anyway, yes. All right, so let us discuss the different reactions. So first, we have your Tanzer. Okay, Tanzer-Gilvard reaction. So your Tanzer-Gilvard reaction, so this is the forward reaction. Okay, so when we say forward reaction, so we have creatine. Okay, so it will be converted to creatine phosphate. Okay, it will be converted to creatine phosphate. So remember that your Tanzer-Gilvard method, so in addition, of course, to your creatine kinase as the enzyme, it makes use of your indicator enzymes. Okay, it makes use of your indicator enzymes. Okay, enzyme system. So in particular, we have the enzymes pyruvate kinase and, okay, pyruvate kinase and your lactate dehydrogenase. Okay, yes, we have your lactate dehydrogenase. All right, so yan. So aside from that, since we are using your lactate dehydrogenase, diba? Remember that your lactate dehydrogenase, this will, yes, this will facilitate the formation of your NAD. Tama ba ako? Yes. Your NAD. Alright, yes. So lactate dehydrogenase. So this will facilitate the conversion of your reduced NADH to your NAD. Okay, so that means, remember, what we can measure is your NADH. So if your NADH is being converted, yes, so if your NADH is being converted, what we are measuring is a decrease, diba? Or a disappearance. Okay, disappearance of your NADH, again, at what wavelength? We have 340 nanometers. Okay, at a wavelength of 340 nanometers. Right. So the other one, we have your Oliver-Rosalki method. So your Oliver-Rosalki method, so this is, yes, this is the reverse reaction in which you have creatine phosphate. Okay, so you have creatine phosphate being converted to creatine. Okay, being converted to creatine. Right, so if you are going to look at the indicator enzyme systems used for your Oliver-Rosalki, in other books pala, they refer to it as your Oliver-Rosalki HESS. Okay, HESS. Oliver-Rosalki or Oliver-Rosalki HESS method. Okay, so this is the reverse method. So again, what are the enzymes that are incorporated? We have your hexokinase, and then the other one is your G6, glucose 6, phosphate, okay, dehydrogenase. Okay, yes, so we have our indicator enzymes. Okay, so actually, the use of this particular enzymes would lead to the conversion of your NAD to your NADH. Okay, so therefore, what are we trying to measure? We are trying to measure an increase, di ba, in your NADH or the rate of appearance of your NADH. Okay, rate of appearance of your NADH. Again, what at what wavelength do we measure your NADH? In this case, we have 340 nanometers. Okay, ayan. Alright, so now let us move on to, I think, konti na lang. Konti na lang talaga. Okay, so next we have our alkaline phosphatase. Okay, so for our alkaline phosphatase, parang feeling ko hindi siya nag-continue. Anyway, tignan na lang natin. Alright, so we have our alkaline phosphatase as the next one. Okay, so for our alkaline phosphatase, so take note that it catalyzes the hydrolysis of your phosphomonoesters, okay, or your organic phosphate esters into alcohol and phosphate ion at an alkaline pH. Okay, so when it comes to the isoenzymes, we have normal isoenzymes, and then we have what we refer to as your carcinoplacental isoenzymes. So normal isoenzymes would include your intestinal, placental, bone, and liver. Okay, and then we also have our carcinoplacental isoenzymes. Regan, okay, Regan. So this is associated with lung cancer. Regan isoenzyme, lung cancer. Nagaw, okay, Nagaw isoenzyme is associated with adenocarcinoma. Okay, Nagaw isoenzyme, adenocarcinoma. And then we have your Kasahara isoenzyme. So this is associated with gastrointestinal cancer. Okay? So, of course, since we are talking about your isoenzymes, it is important for us to be able to characterize your isoenzymes. Okay? So, there are two ways by which we can normally characterize your ALT isoenzyme. We have your electrophoretic mobility. Okay, so for our electrophoretic mobility, sorry, for our electrophoretic mobility, okay, so of course, yes, we start off with your bone. Bone talaga. Okay, ayan. So we have your bone, yes, and then we have your, we have your, okay, we have your, sorry, we have your liver pala muna. Okay, we have your liver, your bone, your placental, and then your intestinal. So this is from your cathode towards your anode. So that means the fastest, diba? The fastest is your liver. Okay, and the slowest is your intestine. Okay, another would be its yes, its resistance to heat denaturation. Okay, so its resistance to heat denaturation. Okay, inactivation by heating, diba? Inactivation by heating. So the most, yes, the most labile, heat labile out of all the different, yes, out of all the different isoenzymes of your alkaline phosphatase is your bone. Okay, the most heat labile is your bone. The most heat stable is your placental. Okay, ayan. All right. So if we are going to list down from the most heat stable to the most heat labile. Most stable is your placental, followed by your intestinal, and then your liver and your bone. So actually in practice class, we only perform your heat denaturation, or the significance rather of your heat denaturation is for us to differentiate your bone and your liver. Okay, yes. So we have to be able to differentiate your bone and your liver. So by the way, heat denaturation class, so this is carried out at 56 degrees Celsius. Okay, for how long? We have 15 minutes. Okay, so 56 degrees Celsius for 15 minutes. Okay? Ayan. Okay, so another way by which we can characterize our ALT is with the use of your L-phenylalanine, okay, your L-phenylalanine and your urea, okay, and your urea. Okay, so when it comes to your urea, yes, so bone is inhibited by urea. Okay, so bone ALP is inhibited by urea as well as your intestinal and also your liver. So for your phenylalanine, inhibits your placenta, your intestinal, and your ray gun. Okay, and your ray gun. All right. Okay. What they ask usually, so of course, aside from those that I have mentioned, so please also include in your review the different substrates, okay, the different substrates that are utilized for the assay of your alkaline phosphatase, okay, the assay of your alkaline phosphatase. So for your Shinawara, Shinawara Jones Reinhardt, it makes use of the substrate beta glycerophosphate. Okay, beta glycerophosphate. And then we have your King Armstrong. We have your phenyl phosphate. We have your Bessie-Lowry-Brock method. So it makes use of your para-nitrophenyl phosphate. And then we also have your Bowers-McComb. Dapat to ha. Bowers-McComb, which makes use of the same as that of your Bessie-Lowry-Brock, which is your para-nitrophenyl phosphate. So they have asked your Bowers-McComb. Okay, so what is the substrate? We have para-nitrophenyl. Okay, para-nitrophenyl. And take note that your Bowers-McComb, this is considered to be the reference method. Okay, the reference method. All right. So highest elevation, or it is used rather, so sige, clinical significance muna. So this is used in the evaluation of hepatobiliary and bone disorders. So just like what I have mentioned, when we talk about your hepatobiliary, diba? Pag hepatobiliary disorders, so what pair of enzyme do we use? We have ALT and GGT. If it is hepatocellular, we have your AST and your ALT. So the highest elevation of your ALT, this is seen in your Paget's disease, or otherwise referred to as your osteitis, osteitis deformans. Okay, so we have your osteitis deformans, or otherwise referred to as your Paget's disease, particularly if we are handling, okay, older people. Yes, it's actually the most common elevation in older people. Okay, ito pa class. Okay, ito pa class. Another. Take note that your ALP, okay, your ALP ha, so it is also, yes, it is also, there is also rather a physiologic increase in your ALP seen in pregnancy. Okay, so it is considered to be physiologic because remember that during the the third trimester of pregnancy, there is already bone formation. Diba? Bone formation starts in the developing fetus. And so, of course, if you are going to develop bones, diba? So this would involve your alkaline phosphatase. So that's why if it will be asked, say for example, in the board exam, which of the following involves a physiologic increase in your ALP? So the correct answer is your pregnancy. Okay, it's normal. Yan. To have an increase. Okay, particularly during the third trimester. Okay. Yes, so now let's move on to the other phosphatase enzyme, and that is your acid phosphatase. Okay, so for your acid phosphatase, so this one naman catalyzes the hydrolysis of your phosphomonoesters into alcohol and your phosphate at an acidic pH. So particularly, we have a pH of 5 to 6. Okay, a pH of 5 to 6. So, when it comes to the specificity of your ACP, so it can be found in greatest concentrations in the following. We have prostate, liver, spleen, RBCs, platelets, and bone. However, highest concentrations are found in your prostate gland secretions and your RBCs. All right, so that's why when it comes to the isoenzymes, okay, the isoenzymes that are clinically significant, we consider your prostatic ACP and your non-prostatic ACP, otherwise referred to as your erythrocytic ACP. Okay, so when it comes to the different or the separation of your erythrocytic and your prostatic, so of course your prostatic is the one that migrates the faster. Yes, so it is more anodal as compared to your non-prostatic or your erythrocytic ACP. So when it comes to the substrates used, yes, so please do not forget for your Bodansky, it makes use of your beta glycerophosphate, your Gutman King Armstrong, Gutman King Armstrong, it makes use of your phenyl phosphate, Babson and Reed, Hudson pa pala. Hudson, we have para nitrophenyl phosphate, and then we have your Babson and Reed, alpha naphthyl phosphate. Roy method, we have your thymolphthalein monophosphate, and Ritz and Gibault, we have 4-methyl umbelliferone phosphate. Okay, so those are the different substrates. Okay, ayan, those are the different substrates. Okay. All right. So, when it comes to its clinical significance, ang pinaka-clinical significance niya is it is utilized for the diagnosis, to aid in the diagnosis of metastatic carcinoma of your prostate. Okay, so prostate cancer in short. All right. And take note that it is also clinically significant in, yes, rape cases. It is important rather in rape cases. So it is the one that we correlate to the presence of seminal fluid. Tama? Seminal fluid, semen pala. Okay? Seminal fluid din naman yun. Okay, so it is the one that we correlate or detect rather to correlate for the presence of semen. Okay? Ayan. Alright, so malapit na tayong matapos. I think last two. Last two for endocrinology. Next, we have your gamma-glutamyl transferase. So for your gamma-glutamyl transferase, I included it because they would oftentimes ask about your gamma-glutamyl transferase. So take note that it is involved in the transfer of the glutamyl residue from your gamma-glutamyl peptides to your amino acids. It is used for the evaluation of your obstructive jaundice, biliary obstruction, and liver cancer. Sorry. And it is the first abnormal liver function test in heavy drinkers. Okay, so let's try to make it simple. Okay, so again, take note that your DGT, this is considered to be the most sensitive indicator of hepatobiliary disease. Okay, and so when it comes to its correlation in the laboratory, it is utilized to differentiate the cause of an increase in your ALP. Okay, it is utilized in the clinical setting to differentiate, diba? Or to provide a differential diagnosis for an increased ALP. Okay, so remember that an increase in ALP, so it would usually be, it would usually be, it would usually either be, it would usually be liver versus your bone disease. Tama? Liver or your bone disease. All right. So say for example, yes, so you have a laboratory result. What you have to look for is your GGT. Okay, what you have to look for is the value of your GGT. So if the value of your GGT is increased, so if you have an increased GGT, so this is hepatobiliary disease, and this involves or this indicates liver. Okay, it is a liver disease. However, if for example, okay, if for example, the GGT is normal, for example, the GGT is normal, then the increase in your ALP is caused by a bone disease. Okay, a bone disease. So aside from that, yes, favorite nila to, GGT, di ba? GGT, whenever you see the term alcoholic or alcoholism in the question, it's automatic your GGT. Okay, di ba? Parang gin tea. Okay, oh, para so that you would be able to remember it. Gin tea. Oh, di ba? Parang si gin tea. I don't know. Yeah, if you have tried but don't try yet. Okay, ayan. All right, so that's for your gamma glutamyl transferase. Okay, so next we have the other enzymes. Wow, 1 hour lang. Okay, other enzymes, we have your cholinesterase, your amylase, and your lipase. You know, ang tinatanong lang nila when it comes to your cholinesterase is enzyme that is clinically significant when decreased. Okay, so this is the enzyme that is clinically significant when decreased. Okay, yes, enzyme that is clinically significant when decreased, we have your cholinesterase enzyme. So take note that your cholinesterase enzyme, so this is associated with your organo, di ba? Organophosphate poisoning or insecticide poisoning. So remember that organophosphate, so this is a common ingredient in your insecticides. Okay, bakit ka naman kasi na insecticide? Besh, you're not an insect. Diba? Okay, so yan. Insecticide poisoning, cholinesterase. Organophosphate poisoning, cholinesterase. Enzyme that is clinically significant when decreased, cholinesterase. Okay, amylase and lipase, these are both important for the assay. Pair of enzymes, di ba? Pair of enzymes that is used for the diagnosis of your acute pancreatitis. We have your amylase and your lipase. Another recall question, what enzyme is expressed in Somogy units? We have your amylase. Okay, so in particular, di ba? In particular, your Somogy units, this is utilized in the saccharogenic method for measuring your amylase. Okay, so the classic, your saccharogenic method, so this is considered to be the classic reference, okay, method for the assay of your amylase. Okay, so classic reference method for the assay of your amylase. Okay, so we have your saccharogenic method. Right? So actually, there are still others, like for example, we have your amyloplastic, your chromogenic, right? And then your continuous monitoring. Okay, so those are the enzymes, yeah, that are commonly asked in the board exam. So I hope I was able to help you. Yes, help you, Kajans. Okay, so I will hand tuloy. Let me just continue na lang kaya. Okay, let me just continue. Ayan, I think I still have time naman. Okay, ayan. So what is this? This is your cardiac, di ba? Cardiac markers. Okay, so we have your cardiac markers. So actually, your cardiac markers are divided into two. So we have your cardiac enzymes, and then the other one, we have your cardiac proteins. Okay, and they are all markers for or markers of cardiac injury. Yes, all right. So first, we have your cardiac enzyme. So historically, ano yung first? What was the first enzyme that was utilized for, yes, that was utilized for the evaluation of your acute myocardial infarction? We have your AST. So actually, in like almost the same time, Ladu, yes, Dalu tuloy. Ladu, um, he was able to identify that he can make use of your transaminases, okay, as serum marker for cardiac damage. Okay, si transaminases Ladu, diba? Kaya nga may pinangalan sa kanya or may nagawa din siyang method. So Ladu, serum mark, he was able to recognize that transaminases can be used as serum marker for cardiac damage. Okay, so it was actually Carmen who developed a rapid spectrophotometric measurement of transaminases that is based on the absorbance of your NADH. Okay, yes. And according to Carmen, siya daw ang nauna. The first biochemical markers, this person was able to discover the first biochemical markers of cardiac damage. Okay, so that's the history of your AST being an enzyme that is used to evaluate your cardiac injury. Okay. However, the problem with your AST is that it lacks specificity. Okay, it lacks specificity. And so it was replaced by another enzyme, and that enzyme is your lactate dehydrogenase. Is lactate dehydrogenase still being used by laboratories? Yes. Okay, so it replaced your AST. Why? Because as compared to AST, your lactate dehydrogenase is considered to be a more sensitive marker of your acute myocardial infarction. Okay, so this is, ito na naman ako, mag-highlight na naman. So actually, it's a faint, very faint po siya. Wait, what will I use? Yellow na lang. So this one. So that one, the gray one, okay, so that shows the pattern of your lactate dehydrogenase. Okay, it shows the pattern of your lactate dehydrogenase. Okay, so your AST is no longer included in this because it's no longer used. It's obsolete already. Okay, yan. Again, the problem with your lactate dehydrogenase is that it is not specific. Why? Because it is only your LB1 and LB2 that are considered to be cardiac specific. Between the two, the more cardiac specific is your LB1. Okay, yes. So there are only two isoenzymes that are indicative of cardiac involvement, right? Yes, and more specifically, we have your LD1. Diba? That's why I discussed a while back your flipped LD pattern, right? In which, in normal serum, LD2 is higher than LD1. However, in the case of your acute myocardial infarction, LD1 becomes higher in concentration as compared to your LD2. Okay, so yan. All right. So before I move on, hirap mag-move on, besh. Okay. Before I move on, when it comes to the criteria in choosing the best marker, the best cardiac marker, ha? Okay, what we want is a very high elevation and an elevation that is fast. Okay, so I repeat, ha, what do we want in choosing the best cardiac marker? What we want is high elevation, high and fast elevation. Okay, high and fast elevation. So in general, this is our basis in choosing, okay, in choosing the best cardiac marker. I think may nakalimutan ako. I'm sorry. Okay, so aside from high and fast elevation, we also want a slow, okay, a slow decrease, di ba? Slow decrease or slow normalization. Okay, so I hope you get what I mean. If there is such a term as normalization. Okay, yes. So we want a cardiac marker that is high, that is, or that has a fast elevation, a high elevation, and we want a cardiac marker that decreases slowly or normalizes slowly. Okay, yes. So if you are going to compare your LDH as compared to your CK, sige. If we want to compare the two, may I use this one, green. Okay. So the yellow one, that's your LDH. Hindi kasi siya masyadong kita eh. And then this black one, that's your, this one. Alright, so the black one, that's your creatine kinase. So as you can see, it goes higher or it elevates higher as compared to your lactate dehydrogenase. So that's why when they discovered your creatine kinase, they were able to find out that it is readily detected in plasma with a higher sensitivity at a shorter time after cardiac muscle injury. Okay, as compared to your LDH. So that's why between your LDH and your CK, which one is more preferred? It's your CK. And in this case, class, we are talking about total CK, ha? Yes, because they were still not able to discover the presence of your CKMB. So, of course, yeah, since we are talking about history, the next thing that they were able to discover is your CKMB. Okay, sorry, we have your CKMB. So, where is our CKMB? Ayan, think tayo. Okay, so where is our CKMB? So, this one is your CKMB. Okay, so is CKMB better than LDH and CK? Yes. Yes. Okay, because it increases more rapidly. Diba? It increases more rapidly and it increases higher as compared to your CK and your LDH. Okay, so that's why among the three, of course, the most preferred one is your CKMB. All right, and specifically your CKMB is the specific isoenzyme in cardiac tissue out of all the isoenzymes of creatine kinase. Okay, so it increases 4 to 6 hours, peaks in 12, diba? Peaks in 12 to 24 hours and returns in 2 to 3 days. Okay, yes. Still, they wanted a better cardiac marker. And so they were able to, yes, to explore the possibility of your cardiac proteins as your cardiac markers because the problem with your CKMB, although it increases faster and it increases higher as compared to your CK and your LDH, it returns to normal fast also. Diba? Okay, so take note that it returns to normal in as fast as 18 to 24 hours. Okay, and by the second day, it is already normal. So what if the patient, di ba, sought medical help 3 days or 5 days after the acute myocardial infarction? Would you be able to detect your AMI? No, because your CKMB is already normal. Okay, so that's the problem with your CKMB. It returns to normal fast. All right. And so, yeah, of course, the search is on for the best cardiac marker. The next cardiac marker that I will be discussing is your myoglobin. Okay. Your myoglobin, it is more sensitive as compared to your CKMB during the first hours. Okay, why? Because it increases faster but not higher. Kasi this one is this one. If you are going to look at it, it increases faster. Okay, it increases faster at a faster rate as compared to your CKMB. It is able to peak class. It is able to peak at an earlier time as compared to your CKMB. Although the peak is not high as your CKMB, still your myoglobin is considered to be more sensitive than CKMB sorry, during the first hours. Okay, so specifically it increases 1 to 4 hours, peaks in 6 to 9 hours, and returns to normal in 18 to 24 hours. Okay, yes. Okay. Your CKMB, parang mali yata yung nasabi ko. Ulitin ko na lang. 4 to 6 hours, peaks. Increases rather in 4 to 6 hours. Peaks in 12 to 24 hours. Returns to normal in 2 to 3 days. I cannot remember what I mentioned. Okay, yan. So, yes. The problem with your myoglobin is that it returns to normal even faster as compared to your CKMB. Diba? Within 18 to 24 hours, it is already normal. So that means after 1 day, myoglobin is already normal. You can no longer detect the presence or the occurrence rather of your AMI. So that's why myoglobin, although more sensitive than your CKMB, so it is not a reliable long-term marker of cardiac damage. Because after 18 to 24 hours, it is already normal. Diba? How would you be able to detect if, for example, the patient suffered from AMI, if it's already normal? Okay, yes, and so the search is on. All right, so the next one is your troponin I. So where is our troponin I? Of course, it's the best. Sorry, nalayan na. Okay, so this is your troponin I, the red one. Okay, so you have there your troponin I. Okay, you have there your troponin I. All right. Your troponin I, as you can see, it elevates the fastest, diba? Among the different cardiac markers. And apart from that, it elevates the highest, slightly higher as compared to your troponin T. So that's why it is regarded as the most sensitive indicator of cardiac injury. Apart from that, the good thing about your troponin I is that it returns to normal quite slow. Diba? Much slower as compared to the other cardiac markers that we have discussed. And this is a good thing. right? Especially if you want to, if the patient rather sought help or went to the hospital to seek medical attention days after the acute myocardial infarction. Okay, ayan. So actually, if I'm not mistaken, that's the gold standard already of your acute myocardial infarction. Okay, so in particular, it increases within 4 to 6 hours, very fast. It peaks within 12 to 18 hours, very fast, di ba? And it starts to return to normal in 6 days. Okay, yes, 6 days. All right. Okay, the problem or if we are going to compare, kasi it's not really naman a problem, okay? If we are going to compare, yes, your troponin I and your troponin T, what can you observe? So this one, yung katabi, the one that is beside your troponin I, that's your troponin T. Okay? Yes. What can you observe about your troponin T? Your troponin T increases slower as compared to your troponin I. However, the good thing about your troponin T is it remains elevated longer and maintains a higher sensitivity after 7 days. Okay, yes, after 7 days, the best marker, cardiac marker that you should assay is your troponin T because it remains elevated longer as compared to your troponin I. So that means, class, it depends upon the situation that is given to you. So if, for example, the patient suffered acute myocardial infarction 5 days ago, 5 days ago, what is the best cardiac marker? Troponin I. However, if for example, the patient suffered from acute myocardial infarction 8 days or 7 days ago, so what is the best? It's your troponin T. Okay, so it remains elevated longer and it maintains a higher sensitivity even after 7 days. Okay, so that's why, yes, in some other references, it is otherwise referred to as a chronic marker, like a marker rather for chronic angina or chest pain, chronic chest pain. So if, for example, the patient has been suffering from chest pain for a lot of days already, then the best marker that we should test is your troponin T for chronic angina, okay, or chest pain. All right. Wow, 1 hour. Okay. Hindi na lang. All right. So next we have our, tapos na. Electrolytes na tayo. And then, oh my gosh, ang dami pa, besh. Okay, next we have electrolytes. So let me just discuss this kasi this is important. One of the questions that was asked in the board exam is about your anion gap. So that's why you should be able to understand your anion gap. I know that you did already your advanced reading. So first we have your electrical neutrality. Okay, yan. Always class, then when we talk about your electrolytes in vivo, di ba? Their concentration would always be based upon electrical neutrality. Okay, yes, because that's the law of nature. You cannot have a big difference in your anions and your cations. Okay, because we don't want to have a net charge in vivo, 'di ba? the concentrations of your cations and anions would always be dependent upon maintaining electrical neutrality. Okay, and of course, when we say electrical neutrality, if we are going to look at the concentration of your cations and your anions inside the body, so they should be equal, okay, or approximately equal to one another. So total cations should be equal to your total anions. Okay, ayan. So of course, basing from this one, from this basic concept, okay, total cations, you cannot measure all of your cations inside the body because that will not be practical for us to be performing in the laboratory. And so, yes, we just consider the major cations and the major anions inside the body. So for our cations, they are represented by your sodium and your potassium. Okay, so in addition to your sodium and your potassium, we have what we call your unmeasured cations. Okay? Yes, because you cannot measure, di ba? It will be impractical for the laboratory to measure all of the cations. And so, the cations which are not measured, which are not measured in the laboratory, we refer to them as your unmeasured cations. Alright, ayan. So this is in order for us to maintain or attain electrical neutrality. So again, this should be equal to, yes, we also have anions, representative anions. We have your chloride and your bicarbonate anions. Okay, yeah. So cation should be equal to the concentration of your major anions plus, of course, it would also be impractical for us to measure all of your anions in the laboratory. And so, the unmeasured anions should be represented in our equation. Okay, yan. So, yes. There are instances when the potassium will not be, will not be given, later we will discuss that. All right, so if we are going to consider your anion gap, okay, yes. Technically speaking, there would be more anions which are not measured as compared to your cations which are not measured. And so, an ion gap, therefore, is represented by this equation. Yes. Yeah. In reality, sorry, the concentration of your unmeasured anions would always be greater than your unmeasured cations, creating now a gap. Okay, an anion gap. Naku ayan. So, if an ion gap is equal to unmeasured anions minus unmeasured cations, then we have to make use of your ability to transpose your variables. So, how can we arrive at this particular equation? So, your unmeasured cations, this variable should be transferred here. Tama, to this side. And then, this ones naman, your anions, they should be transferred to this side. Okay, so if we are going to do that, then our equation becomes, okay, unmeasured anions, di ba? Sige na nga, unahin na nga natin yung, okay, yung let's transpose first your chloride and bicarbonate. Therefore, our equation will now become sodium plus potassium, okay, minus your, okay, chloride plus bicarbonate. Okay, yes. So this is now the first portion of our equation. And then we transpose your unmeasured cation to the other side. So the equation becomes unmeasured anion Okay, unmeasured anion minus unmeasured cation. Okay, and again, remember that your unmeasured anion minus your unmeasured cation. So basically, this is your anion gap. Tama. Therefore, we can say that for the formula of your anion gap or your AG, so this will now be equal to, okay, sodium plus potassium minus chloride plus bicarbonate. Okay, ayan. So take note class that your potassium, nakalagay pala dyan, okay, that your potassium is intracellular. So it is the major, di ba? It is the major intracellular cation. And so, what are we trying to measure ba? Or what sample do we use when we perform electrolyte? It's your plasma or your serum, di ba? It's your plasma. Yes, it's your plasma basically. Okay, yan. So since what we are measuring is your plasma, which is part of your extracellular fluid, and the potassium is intracellular, we can say that your your potassium is a minor component of your serum. Diba? It's a minor component po of your serum. Okay, yes. So it's a minor component of your serum. So that's why in some other references, or actually even in the boards, there is a possibility that they will not include your potassium. And so the formula will now become sodium minus, okay, just your chloride, sodium minus your chloride, and then your plus your bicarbonate. Okay, so this can now be the formula for your anion gap. So how do we determine what formula to use? It depends upon the given. Okay, it depends upon the given. So say for example, all electrolytes are given. So we have values for your sodium, your potassium, your chloride, and your bicarbonate. So you use this formula, the long formula. Okay, you use this one. If, for example, potassium is not given, then you use this one. Okay, or better yet, if, for example, potassium is given, okay, you check the choices. You compute. Yeah, you compute using the first formula and the second formula. All right. So if, for example, your computed value is among the choice, kung ano yung computed value na nakuha mo, and that would be seen in the choices, then that's the answer. Okay, ayan. So another important thing is considering your increased anion gap. Okay, so there will be an increase in an ion gap if, for example, there is an increase in your unmeasured anion or a decrease in your unmeasured cation. Okay, yes. So laboratory error will also result to a laboratory or a falsely increased anion gap. Okay. Yes. So if there is a false increase in your sodium or a false decrease in your chloride or bicarbonate, so this will result to an erroneous elevation in your anion gap. Okay, ayan. So decrease anion gap is seen if there is a decrease in your unmeasured anion and an increase in your unmeasured cation. And when it comes to the erroneous result, the laboratory error that is involved is if there is a false decreased potassium tuloy, sodium, and or a false increase in your chloride or bicarbonate. So another recall question in the board exam, remember that your anion gap is important in the diagnosis of your metabolic acidosis. Okay? Ayan. All right, so now let us go to your bilirubin. Yes. So I will just be presenting the different methods for bilirubin measurement. Okay. So the chronology of events. So this shows how our tests or methods were developed. Okay, in reference to bilirubin measurement in the laboratory. Okay, so the first one that was utilized in order to provide a measurement or for your bilirubin is based on the yellow color of your bilirubin. So remember that bilirubin has an inherent yellow color. And because of this, it was used to estimate its concentration. So remember that they can only estimate because the concentration is just based on the intensity of the yellow color that is produced by bilirubin. Okay, so the first described reaction for bilirubin measurement was developed by Ehrlich. Okay, so of course it is referred to as your Ehrlich reaction, and it was utilized for the assay of bilirubin in urine samples. All right, ayan. So this was developed in 1883. And we now popularly refer to it as the Ehrlich reaction. So the Ehrlich reaction involves allowing bilirubin to react with diazotized sulfonilic acid, which will give rise to a red or blue pigment. Okay, yes. And then after several years, it was Vandenberg who first applied the Ehrlich reaction, this time using serum as the sample. Okay, yes. The problem is that, of course, they were able to discover that bilirubin can exist in two forms. We have your conjugated, and then the other one is your unconjugated bilirubin. And depending upon the type of bilirubin, yes, of course, there is a need for you to incorporate an alcohol, diba? An alcohol to an accelerator rather. So the purpose of your accelerator is to allow the measurement of your unconjugated bilirubin, otherwise referred to as your indirect bilirubin, right? So your Vandenberg incorporated alcohol as an accelerator for coupling bilirubin to diazotized sulfonilic acid. The problem with the Vandenberg reaction is that it made use of an alcohol capable of precipitating urine. Remember that, urine tuloy, capable of precipitating protein. Remember that your protein, it undergoes denaturation and precipitation at higher concentrations of alcohol. So that was the problem in your Vandenberg reaction. Okay, so presence of proteins in your serum will cause turbidity. Yes, and it will interfere with the reading of your reaction. Okay, yes. So that's why it was in 1937 when Malloy and Evelyn developed the first useful quantitative technique. So if you're going to look at the accelerator that is used in your Malloy and Evelyn or Evelyn and Malloy, so they utilized 50% methanol as the accelerator. And the good thing is that it has a lower concentration of alcohol, thus, okay, it does not precipitate proteins. Yes, unlike in the case of your Vandenberg reaction. Okay, yan. Ma'am, why naman in Ehrlich reaction we don't have accelerator? Remember, di ba, in urine samples, the only type of bilirubin that should be present or that is excreted via your urine is your direct bilirubin or your conjugated bilirubin. We don't have unconjugated bilirubin in your urine, right? Yes. So that's why there's no need for you to incorporate an accelerator. Okay, ayan. So another, we have your Gendrasik and Groff method. So instead of 50% methanol, it makes use of your caffeine benzoate acetate as the accelerator. Okay, so what is the method or the reactions, or what are the reactions involved in your gendrasic growth? So your serum or plasma, if it contains bilirubin, so this will react with, or this is allowed to react with your sodium acetate. Actually, your sodium acetate, this is merely a buffer. So it is allowed to react with diazotized sulfonilic acid in the presence of sodium acetate as the pH buffer, and your caffeine sodium benzoate as the accelerator, in order for you to be able to measure your indirect or your unconjugated bilirubin. So this will now form a purple azobilirubin, and again, in the presence of a strongly alkaline tartrate, so this will now form your blue azobilirubin, which is measured at 600 nanometers. Okay? So class, actually, yung ating sodium acetate as well as your alkaline tartrate, so they are merely important in order for us to maintain the alkaline environment that is needed okay, for your gendrasic and growth method. Alright, ayan. And eto class, naitanong kasi to before eh. Take note ha, that in the case of your newborns, there is a very simple procedure that we perform, and we refer to it as direct photometric. Okay, direct spectrophotometric procedure. So this procedure is performed in order to get the absorbance directly, di ba? The absorbance of your bilirubin directly from your sample. Okay, that's why it is referred to as direct spectrophotometry. However, take note that its application is only in newborns. You cannot use it for even for children or for adults. Why? Because of the presence of your lipochromes. Okay, yes, in other age groups. So your lipochromes, a good example, say for is your, di ba, one example of a lipochrome is your vitamin A. Okay, yes, vitamin A, it has an inherent color. Yes, and what is usually the color of your vitamin A? It's yellow or orange. Diba? Almost the same as that of your bilirubin. So that's the problem. Lipochromes, like your vitamin A, so they are present in other age groups, like in children or in adults. So that's why we cannot use them. We cannot use direct spectrophotometry in those age groups. However, yes, newborns, they do not have lipochromes. Yeah, they do not have lipochromes. So we can measure your bilirubin using your direct spectrophotometric procedure, and the wavelength that is used is 455 nanometers. Okay, ayan. Okay, so let us now go to TDM and toxicology. Actually, this is just short. Bilisan ko na. In toxicology, so they would just usually ask about steady state, yes, therapeutic range, yan, yung mga yan. First pass metabolism. So these are important terms, okay? So of course, in addition to this, you have to know your ED50. So this is the effective dose. TD50 is your therapeutic dose. LD50 is your lethal dose. Okay, yes. When we say steady state, so this is this is achieved when the rate of administration equals the rate of metabolism and excretion. Okay, steady state, at which the level of your drug is at an equilibrium. Okay, yes. So we have your steady state. Therapeutic range, so this is the range at which clinical effect is achieved. Okay, yes. So the level of your drug at which it is capable of treating, di ba, or managing the conditions of your patient. Okay? First pass metabolism, so this refers to the hepatic uptake and metabolism of your drugs. Okay, so uptake and metabolism of your drugs, this takes place in your liver. All right, so in addition to that, we also have the different specimens. Okay, so for toxicology and TDM, so we prefer serum or heparinized plasma. So peak sample, this is in general, so this is usually collected 30 to 60 minutes after the dose. Trough sample, trough. This is collected before the next dose. Peak sample, that's the highest concentration. Okay, trough sample, so this is the lowest concentration of your drug. So take note that the gold standard for okay, toxicology and TDM, we have your gas chromatography mass spectrometry. Okay, yan. All right. So in the boards, it's important for you to know how to identify your drugs, whether they are cardioactive, antidepressants, sorry. Okay. Whether they are antidepressants, so on and so forth. So for our cardioactive drugs, sige, hanggang ganun muna. Cardioactive drugs would include your digoxin, procainamide, lidocaine, digitoxin, propanolol, amiodarone, disopyramide, quinidine, and your verapamil. Okay, ayan. Your antidepressants naman, so this would include your lithium, amitriptyline, desipramine, doxepin, imipramine, nortriptyline. Okay, yan. So as long as you know how to classify your drugs, okay, that's okay for me. Antipsychotic, so we have your phenothiazines, your butyrinones, risperidone, olanzapine, quetiapine, grabe naman tomato, aripiprazole. Okay, those are our antipsychotic drugs. Anti-inflammatory, we have your acetylsalicylic acid and your acetaminophen. They are otherwise recognized as analgesics. Okay, yes. Okay. Take note that your acetylsalicylic acid, so this is commonly known as your aspirin, right? And I think I mentioned na aspirin. So this is associated with hepatotoxicity leading to fulminant hepatic liver failure as seen in your Rice syndrome. Okay, yes, it has a serious toxic effect, and this is especially in the case of children. Okay, yan. Another related question was the use of your cough suppressant. Ayan. So it is considered to be a mild analgesic and an antitussive agent. So when we say antitussive agent, it is a cough suppressant. So the correct answer to this one is your codeine. Diba? Codeine. It is a mild analgesic and it is an antitussive agent. Okay. Anticonvulsants, we have our phenobarbital, carbamazepine, phenytoin, valproic acid, ethosuximide, felbamate, neurontin, and topiramate. Okay? Alright. Ganyan na lang muna. Immunosuppressive. We have your cyclophosphamide, cyclosporine, leflunomide, mycophenolate, mofetil, prednisone, and tacrolimus. Dami nito Anti-neoplastic, methotrexate, busulfan. Bronchodilators, otherwise referred to as your anti-asthma. We have your theophylline. And then we have our antibiotics, your aminoglycosides. Vancomycin, this is the antibiotic for your MRSA. Diba? Ano ba ang MRSA? Methicillin resistant? Staphylococcus aureus. Okay, and apart from that, take note that your vancomycin is associated with Redman syndrome. Okay, chloramphenicol. You can encounter this in hematology. Chloramphenicol. This is a drug, diba? A drug, an antibiotic that is associated with aplastic anemia. Okay, so other things that you have to remember. Last two, toxicology. Yeah, of course. We have the metabolite. So metabolite of cocaine, we have benzoyl ecgonine. Metabolite of heroin, we have morphine. Metabolite of marijuana is your delta-9 tetrahydrocannabinol or your THC. Okay, metabolite of catecholamines, we have VMA. Do not forget, diba? Wala lang, hindi siya kasama dito pero sinabi ko yan kanina. Okay, so aside from that, always also remember that. Okay, remember that. Ano pa bang sasabihin? What are the different odors which are associated with your poisoning? Okay, arsenic poisoning, yes, it is associated with the odor of garlic. It is considered to be keratinophilic. So that's why if you're going to use other samples, you can make use of samples that have high keratin like hair, nails, and even your skin. Okay, yes. Cyanide, so of course, this is me, odor of bitter almonds. Okay, carbon monoxide poisoning is associated with cherry red color of blood. It has a higher affinity, particularly 200 times more affinity to hemoglobin as compared to oxygen. Okay, ayan. When it comes to toxicology class, of course I would recommend that you read Henry's. Okay, Henry's po. Ayan. All right, and then this is the last one. We have they asked about this table, so please try to memorize this as early as now. Okay, so they have asked already legally intoxicated. Okay, so please memorize the level of a legally intoxicated person, the alcohol level of a legally intoxicated person. We have 100 milligrams per DL or 21.7 millimoles per liter. Okay, so aside from that, meron pang isa wait mo. Okay, where is that again? Ayon, loss of inhibition. Okay? Loss of inhibition and slight disturbances in equilibrium and coordination. Okay, so please do not forget 150 to 200 milligrams per DL or 32.6 to 43.4 millimoles per liter. Okay, so those were the two that were asked already in the board exam. So of course, if you cannot memorize this table for the board exam, I'm not saying for our exam. For the board exam, just don't forget about your legal intoxication and loss of inhibition. Okay, so that ends our discussion. Bye. Bye-bye. By the way, alcohol is considered to be the most, diba? The most commonly abused substance. It's alcohol. Okay, babu.